All right, guys, welcome to, essentially section 8.3 in the book. We're really going out of order in this chapter just to kind of line things up. I like to do all of the two sample stuff at one time. We just got finished with the chapter with all the one sample, tests, and then the chapter before that was one sample intervals. But this chapter mixes tests and intervals together. So you'll notice in some of the sections, like the last section in this chapter, I just throw intervals and tests all in one. But we're going to start a little slow, where we do intervals in this first section for proportions, and then we do tests in the next section for proportions. And then once we get the feel for that, we'll go and we'll work on means just all in one section. All right, so let's talk about two sample confidence intervals, but specifically for proportions. So suppose we want to compare two populations, and we'll have two parameters in this case. This is going to look kind of similar to what we did, even though we didn't technically have two parameters with the paired data example we did back in the last chapter. But we've got these two completely separate parameters, and we want to compare them and see if there's statistical significance between them. All right, so P1, P2, our parameter symbols will just be P1, P2. If we're ever referring to the statistic itself, we'll use obviously the P hat. That's our symbol for statistic, and then N is our sample size. All right, so just to set this up, imagine we have two schools. School 1, we know 70% of their students did homework last night. In school 2, we know 50%. So suppose a counselor at school 1 takes a simple random sample of 100 students and records the sample proportion that did their homework. School 2's counselor takes a simple random sample of 200 students, so it's a little bit bigger, and records the proportion that did their homework. What can we say about the difference of these two proportions? So what we did down here is we just use Fathom software, which is just a statistical software that will create sampling distributions for us. Like it'll run those samples over and over and over again using that statistical software. Now, here is the sampling distribution for school 1. Right, and we can see down here it's centered at 70% because we, think 70% of the students did their homework last night, and so that's what a sampling distribution would look like. Occasionally it gets really high up there near 85, and then really low down there near 57 from time to time. B is the sampling distribution for school number 2. Their sample, though, in school number 2 was bigger, right? They sampled 200 students in their sample, and we know that the bigger sample we take, the less variability there is in the sampling distribution, aka the standard deviation smaller. So that's why this graph is a lot more compact than the first school's graph. However, in this chapter, we're not necessarily concerned with either of those two single distributions, right? Because what we want to do in this is we want to compare two distributions. So what we did is we took the difference between those two. Let me circle that. And this is the distribution we get for C, is the difference between the two. So P hat sub 1 minus P hat sub 2. And it all kind of makes sense because you look, this thing is centered around 20. Now, that makes complete sense because 70 for the first distribution minus 50 for the second distribution should give us a difference of 20% of people. So we see that's the case. Now, let's look at a couple other things. And you can see here, let me get the highlighter. There's 70 for the first one, 50 for the second one, so of course 20 for our mean. But what you will notice is that the spread, like the standard deviation of this third distribution over here, is a lot more spread out than the second one. It almost actually looks more like the first graph with the amount that's there. And I want to look at you, kind of look at the standard deviations here of these two. So the original school 1 had a standard deviation of about 4.5%, 4.6%, whereas school 2 had only about 3.5%. If you subtract those two numbers, right, so if you take 0.0, let me get a pen here and erase that. So if you subtract those two numbers, so 0.0458 minus 0.0354, you do not get that 0.058. And then, furthermore, you realize, well, wait, 4.5%, 3.5%, all of a sudden our new standard deviation is 5%, almost 6%. How's that possible? Well, a couple rules. Remember that when we are transforming data, when we're trying to combine distributions and stuff we learned back with transformations earlier this year, especially with binomial distributions in Chapter 6, we realized that we never actually can subtract standard deviations, right? That's just not something we do What we do instead is we add them, but then we quickly realize, oh, we don't add standard deviations. What we do is we add variances. So what we do is we take the old standard deviations from each distribution, we square them, add them up, and then of course take the square root of the whole thing to undo that squaring. So we do have to convert those original standard deviations to variances, get them all added up, and sure enough, if you type this in your calculator, you get about 0.058, which then matches that standard deviation for the difference between them two. So those two. Obviously, both of the original distributions are normal. The third one's normal. The center makes complete sense. 70 minus 50 is 20. And then, of course, the spread, well, now the spread makes sense considering that we can't add standard deviations. We add variances. All right, so let's look here on page 2, right? So here's kind of our rules for what we just talked about. Both p hat sub 1 and p hat sub 2 are random variables. So the statistic, the difference between those two random variables, back in chapter 6, we learned that you can just straight up add or subtract the means. Like there's no issue with just, if we're adding two distributions, add the means. If we're subtracting two distributions, just subtract the means. But what we can't do is we can't add standard deviations. We must add variances, and we only add variances, even if the problem is a difference problem. Now, mainly in this class, we're going to look at the difference between two distributions. We want to compare them, and so by comparing, we look at the difference between them. So we're mainly going to be subtracting, but that means, regardless, we're going to add those variances no matter what. All right, so let's look at the sampling distribution. First off, the shape. If we want to prove the shape of a sampling distribution, we need to prove the LCC. However, we have to prove the LCC for both of the original populations we're sampling from. All right, now if we're fortunate, we'll be told that the original populations are both normal, so then we can assume the difference or the sampling distribution for the difference is also normal. And that'll pretty much be our statement now, where we say like, oh, the sampling distribution for the difference is approximately normal. The mean of the sampling distribution is just going to be the two proportions subtracted, and then the spread will, of course, be this guy right here. Now, that calculation looks a little bit different than what I wrote above, because essentially, if you guys remember with one sample, this was we did p hat and q hat. When we were doing proportions back in I guess the past two chapters, that was always a standard deviation calculation. And so essentially what they're doing is they're taking two of those, one for each population, right? Now they have to square them because they're variances. You can only add variances. That obviously does the whole square root. And then, of course, because we squared everything, we need to take a square root to undo that. So at the end of the day, what we end up with is this formula over here for our combined spread for the two distributions. So here it is, kind of all in one visual of what the difference of two distributions looks like for proportions, right, with our standard deviation and our mean. All right. So on page 3 here, let's just kind of go through a few problems to kind of see what we're going to look at. So Nathan and Kyle both work for the DMV, but they live in different states. In Nathan's state, 80% of registered cars are made by American manufacturers, where in Kyle's state, only 60% of registered cars are made by American manufacturers. Nathan takes a simple random sample of 100 cars. Kyle selects a simple random sample of 70 cars, and we're going to let p hat sub n minus p hat sub k, one for Nathan, one for Kyle, be the difference in the sample proportion of cars made by the manufacturers. All right, so what's the shape of the distribution, right? The difference. So what we need to do is we need to look at Nathan and Kyle separately. So let's start with Kyle. He's the first one mentioned here. He has 60%. Oh, I'm sorry. No, let's start with Nathan. He's the first one mentioned. Sorry, I got a little bit ahead there. Nathan, he has 80% of cars. Now, Nathan took a sample size of 100. So we'll do the LCC here. I'm just going to label LCC here just to have kind of like an or a header on this problem. So let's see here, 100 times 0.8, that has to be greater than or equal to 10, which is very easily greater than or equal to 10, right? 80 is greater than or equal to 10, no big deal. And then we need to do 100 times 0.2 is greater than or equal to 10, which means 20 is greater than or equal to 10. So Nathan's good. His distribution passes the LCC. We know it's approximately normal. We don't need to write that, right? Because we're going to write a combined statement at the end about both of them being normal, and then talk about the difference then being normal. So let's do Kyle. Kyle had 60%, and he took a simple random sample of 70 cars. So 70 times 0.6 is greater than or equal to 10. This should work out, mainly because 42 is greater than or equal to 10. And then 70 times 40% is greater than or equal to 10, and that will work out also because that's 28 is greater than or equal to 10. So Nathan, or Kyle also worked out. So that's it, right? So we say by the LCC, the sampling distribution, just going to abbreviate here, for the difference, because we're looking at the difference now in proportions, is approximately normal. And essentially the reason being, you would be welcome to say this if you wanted to expand on that, is because the two distributions by themselves are approximately normal, right? So obviously the difference between them will also be normal. All right, let's find the mean. Now, our notation is going to get a little crazier these days, right? We have our mu for mean, but we need to be specific about what we're finding the mean of. And right now, it's p hat sub n minus p hat sub k, right? So we're going to get real sort of specific with, hey, we're finding the difference between these two, and here's the average. So real easy calculation, though. 80% for one state, 60% for the other. So overall, we should see a difference of 20. Let's find the standard deviation, same notation. And p hat sub n minus p hat sub k. And this is going to equal, well, we got to set up a pretty big problem here. 0.8 times 0.2 over, what was our sample size for him? Was it 100? Yeah. And then plus 0.6, times 0.4. And this is all over 70. And we're just kind of following the formula on the other page. And this comes out to about 7.09%. And there we go, right? So LCC, finding the mean, finding the standard deviation, just worrying about notation, how it's changing up and getting a little bit more complicated because we're doing more complicated problems. All right, so when data comes from two random samples or two groups in a randomized statistic, p hat sub 1 minus p hat sub 2 is really our best guess for the two parameters being subtracted, right? I mean, we don't know the two parameters. That's what we're always searching for in stats. And so we're going to use p hat sub 1 and p hat sub 2 to kind of estimate those. All right, so we're going to build a confidence interval because we're going to try to search for the true difference between these two populations that we're worried about. And this is going to be our sort of template for that. We'll formalize this with equations, or I guess equations here in a second. But it's our statistic, the difference of the two statistics, plus or minus whatever critical value we want. So we're bringing critical values back. It's been, I think, like a week and a half, 2 weeks since we've used one. And then times the standard deviation of the statistic. And again, we know that standard deviation is that big calculation right there. Again, I know I'm throwing all these formulas at you all kind of like making it seem as if you need to know the standard deviation. But to be honest with you, we're mainly going to use, once we get towards the end of this section, we're mainly going to use the calculator to run the confidence interval for us. So these big standard deviation calculations sort of get pushed to the side, as well as the formula, the one that I just highlighted. Like, we don't necessarily need to know that eventually. All right, so let's look at the three conditions we need to check. We need to make sure both distributions or samples are random. We need to check independence for both distributions, and we need to check normality for both distributions this time because, right, we have more to take into account. So again, since we don't know the values of p sub 1 and p sub 2, like the actual parameter values, again, we replace them with the p hat sub 1 and p hat sub 2, and then that, obviously changes our, quote, standard deviation calculation to now be standard error, right? We're pretty much using estimates to calculate the standard deviation, so we give it a new name. Okay, these are the same conditions that we had for the one proportion confidence interval, except we just have to check them twice, right? All right, so here's our formal calculation for a confidence interval. Looks a little bit intimidating, but is really sort of basic when you boil it down. We just need to find the difference between the two distributions we're looking at. So like in the original problem about the schools, that would be 20% right there, 70 minus 50. We need our z critical value. We'll remind ourselves of the most popular ones for 90, 95, and 99%. And then our standard deviation calculation to kind of round out that margin of error. And again, we just practice calculating one of those, so shouldn't be a big deal. All right, so let's just jump into a problem here. We're going to do two problems and pretty much call it at that. So here we go. So many news organizations conduct polls asking adults in the United States if they approve of the job the president is doing. This was back with President Obama years ago. So how did President Obama's approval rating change from October of 2012 to October of 2013? Well, according to a Gallup poll of 1,500 randomly selected U.S. adults in 2012, 52% approved of his performance. And then a Gallup poll of 1,500, another 1,500 randomly selected U.S. adults in 2013, around the same time, showed 46%. So clearly we see a drop in his approval rating, but as a good, statistician, we realize that could just be by chance. I mean, it could just be because of random sampling. But we do want to kind of see, like, okay, is there any... Can we kind of narrow down exactly what his approval rating was with a confidence interval? And then, the future question becomes, is that just chance? Can we run a significance test on this to prove that that drop is statistically significant? But we'll get there in the next section. All right, so let's calculate the standard error in part A for the distributions between 2013 and 2012. So I'm going to do, let me change back to a pin here. All right, so standard deviation, and I'm going to use p hat sub, I guess we'll just do 13 minus 12. So p hat sub 12, p hat sub 13. It'd be in a really good habit of ours to kind of define our parameters before we start the problem. We will obviously do that in a moment. Usually, if you think about a panic problem, the first thing we do is define our parameters. So I'll define p hat sub 13 and p hat sub 12 in a moment, but we use contextual labels too, so I feel like we're pretty safe without having to define them right off the bat. All right, so we'll do this. What was his approval rating for 2000? It doesn't matter what order we add these up, so we'll just go with the 52% first for 2012. And that's the complements, 48%. There was a sample size of 1,500. And then we had, 46% in the next year. And then that's times 54%. Also a sample size of 1,500. So this will give us our standard error. So we calculate that, and we get about 0.0182. Nice. All right. So we got those done. All right, so let's construct a confidence interval. And here's the thing. I really do want to take us through all these steps for this. So we're going to kind of go through panic all the way through. However, part C of this problem is our C step. Is there convincing evidence? So we'll kind of bleed into that step a little bit here. We'll try to set up our P and stuff, A and all that stuff up here. I am going to have a little bit of a hard time shrinking this down because I'm not on Notability doing this, so hopefully I can get this all in here. So the parameter of interest, how do we state this now? Well, think about it. We're looking for the difference between the years, So we're always going to phrase now our parameter as, we're looking for the true difference. So the parameter of interest is the true difference. So we've got the true difference in the proportion of adults, or U.S. adults, who approve or approved of Obama's performance from 2012 to 2013. I've also seen people set up the parameter. While I'm talking here, let me see if I can actually shrink this down a little bit. Oh, I can actually. Okay, hold on one second here. I just need to then, I guess, erase this other part. I might cut this part here, but let's see here if I can. No. Okay, give me 1 second here. Let's just kind of erase this here. Make this a little bit bigger. All right. And then we'll just move this up. All right, cool. Hopefully this can move. There we go. All right, sorry about that. All right, so yeah, we've got the parameter interest, the true difference. Some people will take the time then to actually just go ahead over here, and some people will treat this as their parameter. Well, they'll just say, okay, look, this is, the true, or actually, no, this isn't even the true. This is, the proportion who approved in 2012, and then the same thing down here. And I'm just going to kind of, quickly note that with sort of repeated notation there that we would essentially say the same thing down there, who approved in 2013. Anytime you use a variable, and since we're starting to talk about more populations, we want to be careful about defining them as best as we can. So just get in a habit of kind of just defining as much as you can the things. If you use notation in your problem and you haven't really said what it is, you're probably on the wrong track and you need to go back and define it somewhere. Again, I've seen books, and I think even maybe your book on occasion will write their parameter out using or defining the two things they're talking about in the problem. All right, but anyway, let's get our assumptions. We've got a simple random sample of 1,500 in both years. So this is good, just simply because we don't have to state it twice. If the sample sizes were different, then we would have to say, hey, it's this size for this year and it's this size for this year. But they were both 1,500, so we can kind of get by with just saying that once. All right, we'll do an independence check, 1,500 times 10. Make sure that our population is bigger than that, so that's 15,000. And I think it's safe to assume there were more than 15,000 U.S. adults in 2012 and 2013. Again, we get to sort of skip having to do two checks just because they both had a sample size of 15, so we need to assume they're both 15,000 for both years. However, we're not going to be so lucky with our normality checks since there was a different proportion each year. We're going to have to do two separate normality checks here. So let's get 1,500, and let's start with the 52 and 48% year. So 52, 1,500, and 48. And then I'll also just list the work over here for the other year of 2013. This was, what was this, 46 and 54? Yeah, 46 and 54. All right, we do need to get those numbers just to make sure that we actually know that they're above 10, even though clearly they're going to be. So I got 780 for this one, which that's fine, and 720 for this one, that's fine. And then over here I get, what do we get, 690 for this one. And then of course 810 then for that one. So yeah, we're good to go. Everything seems good. And so by the LCC, the difference, or let's say actually, sorry here, not the difference, the sampling distribution for the differences or difference in proportions is approximately normal. And there we go. All right, so lots of checks. Things are really kind of getting a little crazy with the checks that we have, but that'll take the most time on the problem. From this point forward, we get to kind of just do some math and move on here. All right, now we're switching this to a two sample because it is. We've got a sample from 2012 and 2013. This is a Z interval, mainly because we're working with proportions, so we will always use Z with proportions. And for a difference in proportions. And it's not a test, so we don't need to state our alpha value. Nothing to say there. All right, so let's get our I step here. We are working, what is our confidence interval here? We are with a, oh, we don't say. So actually, we're going to assume it's a 95% confidence interval. So our Z critical value, right? We need to pick, oh, no, I'm sorry. We say it's a 90%. I just caught that all of a sudden. We say it's a 90%. So our Z critical value is 1.645. Again, remember 1.645 for 90, 1.96 for 95, and then 2.576 for 99. All right, so there we go. There's our Z critical. We need that. We need to calculate what P hat sub 13 minus
p hat sub 12 is. We haven't even really calculated this yet, our mean. And that is, what were our two proportions? They were 50, what were they here? 52 minus 46. So 52 minus 46. And actually, we went the other way, so I need to flip-flop this around here. We went 2013 first, which is actually the lower proportion, so 46 minus 52. And that won't make a difference. I mean, certainly your confidence interval will come out the other way. If you go the other direction, you'll get just a positive interval instead, which is totally fine. You just have to interpret it, differently. So let's set that up. Our interval is negative 0.06 plus or minus our z critical value of 6.45. And then, of course, our standard deviation, which the reason I had you do that in part A is so we could just put 0.0182 right here. You would need to calculate that in this step if we had not done it in part A. All right, our interval comes out, let's see here, to negative 0.0896 to negative 0.0304. Yeah, so we actually think, and we'll go in and draw a conclusion here in part C, but, did it change? And certainly it seems that it did, only because, 0 is not in the interval. 0 would be like no change in proportion. These are clearly both negative bounds or negative values on the bounds of the interval. So, yeah, it looks like his approval rating did drop, actually, somewhere between like almost 3% to 9%, and we think the true proportion's in there. So actually, let's draw that conclusion. I told you this step's going to sort of bleed into part C here. So we are 90% confident. All right, so we're 90% confident that the true difference in the proportion of U.S. adults who approved of Obama from 2012 to 2013 is, and we can say is between or is captured by the interval from, what was our interval here? Negative 0.0896 to negative 0.0304. Right, so, do we have convincing evidence that it has changed? Yes, to answer the question, 0 is not in the interval. And 0 would be the only reason we would suspect it hasn't changed. So there we go. Cool. So let's look at the next one real quick. And I'm actually going to go through this one because I was looking at the time on this video. This problem took about 13 minutes after it was all said and done. But let's flip over to the next one real quick. And I'm going to go through it very, very, very quickly because we're actually going to use our calculator on this one to do a lot of the work for us. Of course, we'll have to set up our assumptions and everything. But other than that, we can really speed things up. All right, so in this one, we have two groups of 40 randomly selected students who were selected to be a part of a study on dropout rates. One group was enrolled in a counseling program designed to give them skills needed to succeed in school, and the other group was offered no counseling. 15 of the students who received counseling dropped out of school, and 23 of the students who did not receive counseling dropped out. And we want to build a 90% confidence interval for the true difference between the dropout rates between the two groups. All right, so the first thing we're going to kind of get in the habit of doing, like I said, is defining what P, our two separate parameters are. I'm thinking to do C for counseling and maybe N for no counseling, or you could do like NC or something like that, but one variable is good enough. While we're at this, we'll also calculate those proportions too. But this is the, well, what is this here? This is, what do we have, 15 that dropped out of 90, and that is 0.375. And then we've got here, let's see, 23 out of 90, which is 0.575. All right, so we've got our two proportions. And just so we know what P C is and P is, and I'm going to define these as our parameter here, P sub n. This is the true proportion who, or I guess, yeah, the true proportion of dropouts with counseling. And I'm going to have to squeeze that in there. There we go. Just barely. And then this is the true proportion of dropouts without counseling. If it came to the AP test, make sure you're writing this out just so they know and you're not being shorthanding like this. But, you know, for time's sake, I didn't want to keep you on the video for longer than I needed to. In your notes, you're welcome to write it all out too. All right, we've got to get our parameter, like the actual thing. And like I said, some people will use those two things we wrote up above, but we haven't mentioned that we're looking for the difference between the two yet, so we need to say that somewhere. You can use notation to say that, so you could do like literally, here, let me show you what I mean. Let me erase this parameter here real quick. You could say then that at this point, let me define P sub D, and what that is, and you can go in any order you want, but that's P sub C minus P sub n, and this is a great way to communicate your parameter. In fact, actually, I think just for the sake of this problem, let's stop here. You'll notice on occasion I'll actually write out that parameter in words. So, for example, I might say like the parameter of interest is the true difference in the proportion of dropout rates with counseling versus without, you know, and actually say what that true difference is. But notation is just as valid. So here we go, right? All right, let's get our steps here, our checks. We have a simple random sample of, did we have 40 students? Yeah, we had 40 students in each group, 40 in each group. So again, we get to skip that step there. And then that's good that they were the same size, because then we can just say, look, 40 times 10 is 400. It is safe to assume there are more than 400 students to select from for each group. They were at the same school, so it wasn't like 400 from each school, so we just had to say 400 for each group. And that's fine. And then we have to do our normality checks. So 40 times, what was our first rate? 0.375, and that was the importance of calculating that early on. And that's going to come out to 15 is greater than or equal to 10, which is good. And then we're going to have to do 40 times the complement of that, which is 0.625, and that comes out to 25, which is greater than or equal to 10. And then we'll do the same thing for the other one. 40 times our other proportion of 0.575 is greater than or equal to 10. Which 23 is greater than or equal to 10, so we're good there. And then 40 times the complement of that, which is like 42.5%, is greater than or equal to 10, which that one checks out to 17 is greater than or equal to 10. So we are golden, by the LCC. And let's speed this up a little bit, just the same statement we made on the last problem. I know you guys will probably, I encourage you to write it out just because I think it's worth you practicing that statement again and again. So go back up to the other problem, look what we said, and see if you can replicate it on this one. I'm just saving time on the video for your sake. So, all right, let's get in here. It's a two-sample test, a two-sample interval. Is the interval for a difference in proportions. And let's run this guy on the calculator. So step I. Step I can be completely done in the calculator. We'll go to the stat key and over to tests. And then we just got to find two sample. We need to look for the number 2. We need to look for the word proportion. And we need to look for interval. So you kind of scroll through. The first thing I see is like two sample tests. And then I get down to two sample Z interval and two sample T interval. I'm looking at 9 and 0. However, those don't use the word proportion, so those are for mean problems. So I keep scrolling down, and finally I find it as option B. There's the 2. It's got the proportion. It's Z. It's int. So we're looking at option B here. And it's going to ask for several things. It's going to ask for X1 and N1. Those are the amounts. So in other words, we had 15 people drop out of 90 for our first sample. And then the other one, we had 23 drop out of also, not out of 90, out of 40, sorry. And then out of 40 for the other one too. I think, did I And I'm sure some of you guys are like, how did he get those numbers up here? So you've probably been wondering a while and haven't had a chance to go back and correct it. I put 90 here, and that would get a little confusing. These are actually 40 and 40. All right, sorry about that. I'm sure that's like 5 minutes later, and you're still trying to figure out what just happened there. I just typoed and saw the wrong thing. All right, so with that being said, x1 is 15, n1 is 40, x2 is 23, and n2 is 40. Let's adjust our confidence level to 90%. I'm also just double checking that I didn't use 90 anywhere else on the problem that I just, yeah, we're okay. All right, let's hit calculate, and we get our interval here of about negative 0.3799. I mean, you could round that to negative 0.38 if you wanted to. I'm just going to write the whole thing though. So negative 0.3799 to negative 0.0201, and call that there. Now you'll notice they mentioned p hat sub 1 and p hat sub 2. I already have those listed up here. If I didn't have those listed anywhere, I would absolutely need to write those in this step. Pretty much I told you earlier, I said if you're going to use a calculator, just make sure everything that comes out on this menu you're currently looking at is on your page somewhere. So we don't even have the sample sizes. That's how like specific I am. I like to list just everything. You know, I feel like almost with the calculator, you're skipping so much work that I'm at least going to do that part. So there we go. All right, we are 90% confident. I'm going to write this one a little bit differently than the way I wrote the last one. The interval from negative 37.9, well, 0.3799 to negative 0.0201, okay, captures the true difference in the proportion of students who dropped out with counseling versus without. And clearly there was a difference. Zero's not in this interval, so it looks like without counseling, people were more likely to drop out. Now, we don't have a follow-up question about that like we did on the last one, but that's the case. All right, so there it is. There's everything. Tonight's reading quiz, number 57, super short. It's 2 questions. And then tomorrow's is also on proportions too. I'm going to have us get into tests just briefly tomorrow, but tomorrow's reading quiz is longer. And so I will keep the video shorter tomorrow so that you can knock the reading quiz out in class. But good luck. Let me know if you have any questions. You can shoot me an email and I'll try to respond. But I will see you all tomorrow for tests.